All right. So today we get to finish off this chapter. So we had left off, we had just finished talking about shaping and chaining, and now we're going to talk about operant extinction. And so we've already talked about extinction as it pertained to classical conditioning. So that was a situation where we had our conditioned stimulus presented in the absence of the unconditioned stimulus. So you're ringing the bell without giving the dog food, and you see a gradual reduction in that conditioned response. So we would see less salivation as we have those things sort of unassociated. For operant extinction, this concept is fairly similar. So this is a weakening and eventual disappearance of an operant response because it's no longer followed by a previous consequence. So this would be like a rat pressing a lever in a box to get food. If they're used to pressing that lever and getting food, if they push it and then no longer get food, then they're going to stop pushing that lever. But there is something that makes this just a little bit more complicated than our classical conditioning extinction. And this is the addition of what's called an extinction burst. And that's a temporary increase in responding before we see the resulting decrease. So this would be a time where we have sort of emotional and aggressive responding in higher rates than normal. And so what this would look like, if we hop to our next graph here, this looks kind of similar to the diagram we saw for classical conditioning extinction. And so on the bottom, we still have time. Here it's days instead of trials or whatever else we've used in the past. And then on our vertical axis on the Y here, we have text message frequency. So this is an operant behavior. So we could use lever presses if we were looking at a rat in an operant box, but this one is set up looking at, so you text your friend. And so when you send your friend a text, they text back. That's our setup. So your behavior is sending a text, and the consequence is that you get a text in return. So during our normal period, during regular reinforcement, you send a text, you get a text back. You typically send about 4 texts a day, no big deal. But when we enter extinction, maybe you send your friend a text and they don't respond. So you send another one and another one. Maybe you're angry that they're ignoring you, so you send a lot more texts. That would be an extinction burst. If they're still not responding, then you would probably start responding less and less and less until you no longer text that friend. So if this is our rat in an operant box, they press the lever, they get food, we enter extinction, and pressing the lever no longer gets them food. They're going to press the lever a lot. They're going to press it aggressively in the hopes of getting the system to work again. And eventually they figure out that they're not going to get food anymore, so they lose interest and they stop pressing the lever. Same basic setup, just a different operant behavior. Our next slide here is looking at a proper term for something that we've kind of been discussing already. So the concept here is a discriminative stimulus. So this is any stimulus that signals the availability of reinforcement. So we've mentioned one of these already. We talked about a cue light. So in an operant box, we have a red light. And when the red light is on, it tells our chickadees that if they make an operant response, they might be reinforced with food. If that cue light is off, it's off because the system isn't ready for the next trial. So if the bird made that operant response, they're not going to get reinforced. So that light tells us what the conditions are and what the result of doing that particular response would be. So it's a discriminative stimulus because it helps us discriminate between times when we should receive our reinforcement and when we will not receive reinforcement. We can also talk very briefly about generalization and discrimination again. We mentioned generalization and discrimination in regards to classical conditioning. So that was that diagram where we had a vertical line, a diagonal line, and a horizontal line. And we were looking at how much of our conditioned response was produced to each orientation of the line. If we take that exact same graph and change it from a conditioned response to an operant response, so if instead of looking at how much saliva does the dog produce, or how much do they jump in response to something, what if we change it to rate of pressing a lever, or rate of pecking a screen? That would be the same basic relationship, where if we see that we have similar responding to a vertical and a diagonal line, then we can say that the animal is generalizing. They're treating the vertical and the diagonal line similar. If we see that more steep curve, where we have lots of responding to the vertical line, but very little responding to the diagonal, we can say that the animal is discriminating between them, where they treat the vertical line differently than the diagonal line. So same basic concept, same mode of application. We're just talking about an operant response as opposed to a conditioned response. So that's why this doesn't get its own slide. We're just sort of remembering something we've already talked about. All right, next slide is sort of another little bit of terminology here. So we can talk about reinforcing and punishing, but we could also refer to the particular stimulus. We might call it a reinforcer or a punisher, depending on what role it plays. So if it's a stimulus or an event that increases the likelihood of a behavior, then we would call it a reinforcer. So food is a good example of a reinforcer because it makes you more likely to do that behavior so that you get more food. A punisher is the opposite, so a stimulus or event that decreases the likelihood of that behavior occurring in the future. So a loud, scary sound would be a punisher. And we can also talk about these as being primary or secondary. And like I said before, when we were talking about sort of reinforcement versus punishment, most of what we're talking about going forward, we're only going to frame it in terms of reinforcement and specifically positive reinforcement, not because any of this doesn't apply to all of the other types of sort of reinforcement and punishment, just because it's easier to grasp the concepts with positive reinforcement. If you go on and continue studying learning, you can go into more in-depth about punishment and things like that, but we're going to keep it a little bit more straightforward because there's a lot of terms here. But if we talk about a primary reinforcer, it's kind of like when we were talking about something that was unconditioned or unconditional in our classical conditioning. So a primary reinforcer is something that we already know something about. It's already reinforcing. So food is a primary reinforcer. You don't have to teach a rat that food is a good outcome. They get food and they're going to want more food right off the bat. It's something natural and innate. But we can also have secondary or conditioned reinforcers. And these are reinforcers that on their own don't mean anything, but we can learn to associate them with something. So the best example of a secondary reinforcer is money. So money on its own, the pieces of paper with numbers printed on them, doesn't mean anything. But you learn that you can use money to buy things. So you can use money to go get food. So it becomes reinforcing because of what you've learned about it. So if it's something that has sort of an innate pre-existing quality that makes it reinforcing, then it's primary. And if it's something you have to learn about for it to be reinforcing, then it's secondary. And most of the time we're going to look at things like food and water for primary and things like money or tokens for secondary, things that you can exchange to get other things. All right, next we're going to talk about schedules of reinforcement. So far we've kind of assumed that when the rat presses the lever, they get food. And assumedly, every time they press the lever, they get food. But of course, in real life, this is not what we encounter. Every single behavior does not always reliably produce a particular response. So we're going to distinguish between continuous reinforcement, where every response will receive reinforcement, and intermittent or partial reinforcement, where not every response gets reinforced. So partial reinforcement would be like every third time you clean the kitchen, your mom says thank you. But sometimes you clean it and she doesn't even notice, but you're still going to do it because every once in a while she'll say thank you and it makes you feel good. That would be partial or intermittent reinforcement. And so similar to when we were looking at our positive versus negative reinforcement versus punishment, we have another setup where we're going to ask 2 questions, and then we're going to combine our answers to give us 4 possible responses. So the first of our questions, when we're trying to identify what kind of partial reinforcement we have, we're going to ask, is it fixed or is it variable? Do we have a hard rule, or is there some variability, some flexibility in what's going on? So if we have a fixed schedule of reinforcement, then we're saying that reinforcement is going to occur after an exact number of trials or an exact number of responses, or after an exact amount of time has passed. So with our rats in an operant box, every 10th lever press gets food, or the first time they press the lever after 10 seconds has elapsed. Those would both be fixed schedules of reinforcement, because we know after 10 seconds, you can get that reinforcement, or after 10 presses, you get that reinforcement. There's sort of a hard line there. If we introduce variability, then we have variable reinforcement. So this is usually when we talk about an average number of responses or an average amount of time having passed. So if we say that the rat gets food on average after 10 lever presses, plus or minus 4, that means that the rat might get reinforced anywhere from 6 presses all the way up to 14 presses. So there's a lot of variability there. They can't be certain when they'll be reinforced, and that's going to affect their behavior. So that's our first question. Is it a hard rule or is it variable? Is it fixed or is it variable? Our next question is, are we dealing with numbers or are we dealing with time? So is it a ratio or is it an interval? So ratio is dealing with the absolute number of lever presses or responses in general. It might be presented as a ratio, it might be presented as a percentage. But if we say every 10th lever press, they'll be reinforced, that is a ratio schedule of reinforcement. For interval, if we say that a certain amount of time has to elapse before they receive reinforcement, then that is interval. So the first time they press a lever after 10 seconds passes, that's an interval schedule of reinforcement. And of course, we can stick these all together. So we can have a fixed interval. So we specifically say that there's no variability. So after 10 seconds have passed, the next lever press gets the rat food. If we have a fixed ratio, we're saying that we have an absolute rule. Every 10th lever press, the rat gets food. On the bottom are our variable schedules. So variable interval would be that after 10 seconds plus or minus 3 seconds, the rat would get food. And then variable ratio is every 10 lever presses plus or minus whatever number, 3 presses. So if we introduce that range, we're talking about variability. And if we have something that is sort of an exact number, then it's fixed. And then we can talk about intervals for times and ratios for quantities. So those are our 4 different possibilities. And as I hinted, different schedules of reinforcement are going to end up producing different patterns of behavior, different patterns of responding. And we can see this illustrated really nicely on this slide here. So on this graph, along the bottom, we have time. So our standard along the x-axis as always. And on our y-axis, we have cumulative number of responses. So this is sort of a running tally of how many times the rat has pressed the lever, or the pigeon has pecked the screen, or whatever it is that we're looking at. And we're going to look at each line individually and sort of talk about what's going on. So first, we're going to look at the red line. So it's labeled VR. That tells us it is a variable ratio schedule of reinforcement. So variable, meaning that it's not going to happen at a predictable interval or a predictable sort of span, I guess, doesn't refer to anything. And then ratio, we're talking about number of presses. So if we look at the little ticks that come off the side, those little tally marks, those are showing us when the rat receives reinforcement. So each tick mark is the delivery of food. And so it's variable, so they're not evenly spaced. The rat's going to get food at different times after different amounts of presses. And so that makes sense. And ratio just tells us that we're specifically looking at number of lever presses. So this is a straight line, and that kind of makes sense. If we anthropomorphize the rat a little bit and talk about what they're thinking about, maybe we say that, sometimes when the rat presses the lever, it gets food, and then presses the lever, it gets food very quickly thereafter. So it makes sense to continually press the lever. Because we're specifically looking at number of lever presses, the rate at which they press the lever is directly tied to how quickly they get food. So it makes sense that they would be highly motivated to press the lever quickly. So they would press quickly and constantly because they don't know when it's coming next, and the faster they press it, the faster they get food. So we tend to see a straight line because there's no predictability here, and we tend to see a very steep slope because they're motivated to press the lever as quickly as possible. If we move over to our blue line, that's a fixed ratio. So now that it's fixed, we have some certainty on when food will be delivered. And we'll notice that our line ends up sort of plateauing or stepping off after each delivery of a reinforcer. So whenever the rat presses the lever enough to get food, as soon as they get food, they stop pressing the lever. And so if we think about this as every 10th lever press gets food, they've gotten food, they know that the next 9 presses are not going to lead to food. So they're not really motivated to keep pressing. They're going to eat their food until they're sort of wanting enough to press the lever, even though they know they won't get food, before they get food again. So we see those steps because once they've gotten food, they know that their next trial, their next response won't get them food. So they take some time before they start up again. So if we see a nice distinct step like that, that's telling us that we're looking at a fixed ratio. Next, we have our variable interval. So similar to the variable ratio where there's lots of unpredictability here, but now we're looking at the amount of time that's passed. So in the ratio one, how rapidly they press the lever is directly related to how quickly they get food. With the intervals, though, it's the amount of time that's elapsed. So whether they're sitting there pressing the lever really quickly or whether they press it really slowly doesn't really matter. We care about the amount of time that's passed. So we're typically going to see, again, a straight line because it's variable. We don't know when we're getting reinforced next, but we see that the slope tends to be a lot less steep. And that's just because there's a disconnect between the rate at which you press the lever and when the food is delivered. So if we're telling the difference between our variable ratio and our variable interval, the ratio will be steeper just because the faster you press it, the faster you get food. And then our last one is our fixed interval. So this is after a certain amount of time has passed, the next time you respond, you get food. And this one has another distinct pattern. We get to see this sort of scallop pattern. And what's going on here is the same basic concept as the fixed ratio, where as soon as they've received food, they know that they're not going to be getting food for a while. But we see this curve instead of our sharp step, specifically because animals, humans included, are really bad at telling time. So we're really bad at judging how long since an event elapsed. So what we see is right after they get food, there's no responding. And then as more time passes, they check more and more. So we see more responding as we get closer to the next time that they get food, because they're not sure when it's been long enough. And then when they get food again, they're going to stop again. So we see sort of that ramping up in responding, where they respond more and more as we get closer to the right time until they get their food and they stop again. So we see this sort of general pattern for all of these lines, no matter which organism we're looking at for the most part, and across different kinds of responses. It's a lot easier to talk about sort of rats and food. We can look at pigeons and food. We can look at all sorts of different things, but those are the standards. Okay, and then of course, if we've talked about these 4 options, which one is the best method? And always, the answer is that it depends. So it depends on what we're aiming for. So if we talk about continuous reinforcement, that one's a good one because every single time you press the lever, you get food. We see really rapid learning because it's a lot easier to see the connection between the behavior and the outcome. The consequences are a lot easier to see because it happens every single time. So we learn a lot faster. But as a disadvantage when that happens, we notice right away as soon as extinction begins. A single trial where we don't get food is really important if we've been pressing the lever for days and always get food. So we'll go through extinction very, very quickly if we use continuous reinforcement. So it's beneficial if you need them to learn quickly, but it's not going to stick around as long. Partial or intermittent reinforcement, any of our 4 options are going to be better than continuous reinforcement if we're focusing in on sort of persistence through extinction. So we take a lot longer to learn because we don't have that direct connection every single time between the response and the outcome, but we are used to the fact that some trials don't get the response or don't get the outcome. So sometimes you press the lever and don't get food. That's what it is with partial reinforcement. And especially our variable types of reinforcement where there's an unpredictability there, it gets really, really hard to tell if you're in a situation of extinction or if you're just really unlucky and you're in one of those really long periods between reinforcers. So at the bottom, we kind of have a visual representation of that, where if green is when you get reinforcement and white is no reinforcement, during continuous, it's all green. So a single white stripe is very noticeable. With intermittent, you have some green and some white, so it gets a lot harder to tell the difference between sort of spaced out intermittent and actual extinction. So it's going to last a lot longer if you've learned through some kind of partial reinforcement. And specifically, our variable ratio schedules are the ones that are the most resistant to extinction. And when you look at researchers, we actually pick and choose which type we use based on the setup. I'll talk about it on Friday, but within our blackcap chickadees, we start with continuous reinforcement because it's hard enough to teach them anything. So we want them to learn as quickly as possible. And once they learn the association, then we slowly transition them over to partial reinforcement. So we get them used to the idea that not every single trial gets them food, but we started with continuous because we wanted them to learn as fast as possible. Okay, so that's the end of operant conditioning. So let's take a moment and actually talk about how do we tell the difference between operant and classical conditioning. So this chart here is a really great way to sort of focus in on a couple of key points that differ between the two. And if you're the kind of person who likes videos, I also have a link to a YouTube video that talks about both types of conditioning, so you might find that useful as well. I just include that whenever I teach this topic. So let's look at the first of our things to consider here. And this is our controlling stimulus. So what stimulus is sort of setting this up? In our Pavlovian or classical conditioning, our conditional stimulus is the thing that's eliciting our conditioned response. So that bell that the dog has learned something about is what leads them to salivate once everything's been learned. In operant conditioning, it's our discriminative stimulus, our antecedent, the thing that tells us that if we make the response, we'll get our reinforcer now. So that's what starts it off. When we look specifically at our learned behaviors, in classical conditioning, we're focusing on involuntary behaviors, things that are elicited, things that happen automatically. So a dog doesn't choose to salivate. They're just going to do it. It's going to happen automatically. But in operant conditioning, we would say instead of elicited, that the behavior is evoked. It's something voluntary. It doesn't happen automatically. When we look at our important stimulus, so what is it that we're starting to learn about? In classical conditioning, it's our unconditioned stimulus. We start knowing about our food, and then we share what we know about our food. We're going to link that to what we learn about the bell. In operant, what's important is our outcome or our consequence, our reinforcer or punisher. That's going to influence whether we do the behavior more or less. Next question is, does the behavior change the likelihood of the consequence? So this is something that ties straight into sort of operant conditioning and especially our law of effect, where if you do a response, it's going to make that outcome happen. It's going to cause that consequence to occur. That's not mentioned at all in classical conditioning. So the dog salivating doesn't mean that they're going to get food. There's no relationship there. So if we talk about their response leading to something happening or changing the likelihood of something happening, it's always going to be operant conditioning. When we talk about what we've learned in each of these processes, classical conditioning is that link between our conditioned and our unconditioned stimuli. So we learn that association between two different stimuli. In operant conditioning, we learn about our antecedent, our behavior, and our consequence, or our stimulus, response, and outcome, sort of that three-piece flow chart that we were looking at. And then the last one is, can it add a new response to our repertoire? In classical conditioning, if you think about it, the dog salivating, at the beginning they're salivating to food. At the end, we have the exact same behavior. They're still salivating, but to something new. So we're not adding a new behavior, we're getting them to do the same behavior in a slightly different place, or time, or to whatever. In operant conditioning, we can have new responses. So we can get a rat to press a lever or a pigeon to peck a screen. So we see changes, new things are happening. So those are some of the key points. And you can look at sort of all of these to help you decide, is this situation classical or is it operant conditioning? So just a nice shortcut to take a look at. All right, so what we've been talking about so far has been really heavily focused on the interaction between our environment and what we learn by interacting with our environment. We've looked at behaviorists and radical behaviorists. And you might have noticed that we've been pretty severely lacking on what's going on internally. So we're going to take a brief dip into cognitive psychology and specifically social learning. And that's how we're going to wrap up the chapter. So for cognitive psychology, Tolman is one of our big names here. And so Tolman said that our explanations for behavior should include more than just environmental stimuli, and it should also include more than just publicly observable behavior. So he was fed up with all of this classical and operant conditioning where you were looking at something observable in your environment and something observable that you do in response to it. He wanted to look at things that were going on internally. What about what's going on in your head? What about your thoughts? What else is happening? What else can we look at? And this is what pushed that advancement of cognitive psychology. And so specifically, we're going to be talking about a concept called latent learning. And this is when you learn a behavior, but you don't actually demonstrate that you've learned that behavior until the opportunity presents itself. So until you are motivated or reinforced for performing that behavior, we have no way of really telling if you've learned anything. And this was tested mostly in terms of what's called cognitive maps. So our mental representations in our minds of our environment. So the idea here is that if we're interacting with an environment, we might not be able to see any change in behavior because we're just wandering the environment. But we would be building up a map, a representation of that environment. And then if later it mattered what we knew about that environment, we could then see changes in behavior after the fact. So an example that helps illustrate what I'm talking about is Tolman's looking at T mazes, or specifically strings of T's intersecting in rats. So if you've ever worked with rats or heard of people working with rats, especially with navigation, they love their mazes, and they call them mazes despite the fact that most of them are fairly simplistic. So they have a T maze, which is what it sounds like. It looks like a capital letter T, where a rat runs down a hallway and then is faced with the choice to turn left or right, and one or the other would be correct. We also have plus mazes, which would be what you'd expect, a big plus. You can also have radial mazes, which is sort of like multiple arms. So it's kind of deceiving to have them called mazes. But this one here is a series of those T intersections all stacked together. So this one's closer to a maze than most rat navigation research would be. And so if we look here, there is a starting point and an end point. And so there is sort of a right and wrong way to turn if you were trying to get from the start to the end. But if you have a rat who's presented with the opportunity to wander around in tunnels, in mazes, and there's nothing for them at the end, there's no motivation for them to find that end. So Tolman would allow rats to hang out in the maze, to wander around. They like tunnels, so they don't need to leave. There's no motivation to go anywhere, so they would just experience the maze. And if they were learning anything about it, if they were forming a cognitive map, then we would see changes in their behavior later when there was an opportunity or when there was motivation to see that improvement. So the idea here is that there were some rats who had experience with this maze and knew what was going on, and then there was a control group who hadn't seen the maze before. And so if we have the group that theoretically has formed a mental map, and now we introduce some kind of reinforcer, some kind of motivation. What if we put food at the end? Well, then the rats would have reason to get out of the maze more quickly. So if we place food at the end and then look at how quickly the rats that have a theoretically mental map of the maze, they should get out faster than the rats who have no experience with the maze, which is what they find in pretty much all of their different iterations of this. So that's evidence for A, cognitive maps, because they had learned something while wandering around in the map, because they would turn the right way more often than the wrong way to get out. But we also see evidence here for latent learning, because they didn't show any difference in their behavior at the start, but once they were motivated to get out, then they showed that improved speed. They learned and changed their behavior to escape more quickly when there was reason to. So this gives us evidence for both of those concepts. So next, we're going to get into social learning proper, or sometimes called observational learning. And our big name here is Albert Bandura. And so Bandura focused on studying kindergarten students, trying to establish observational learning as a concept. And this kind of makes sense. We can think of examples of classical conditioning and operant conditioning in our own lives. We behave in particular ways because of associations that we've made, or maybe we do certain behaviors because our parents encouraged it, and we avoid other behaviors because those were discouraged. So we can see those pretty clearly, but a lot of our learning actually comes from watching our environment. So with social learning, we start understanding what we should be doing by watching others. And a great example of this that I experienced was coming back to campus for the first time after we were online for a little bit. I had no idea what the new setup was, and I wasn't sure what to do. So I sat in my car for a little while and I watched where other students were going. Where was the line forming? What did people have out when they got to the door? So I watched other people get into the building, and then I copied their behavior so that I could get into the building too. So I exhibited social learning or observational learning by watching somebody else achieve their goal, and then I copied it to achieve the same goal. And we could even call this vicarious conditioning. So if we're looking or watching someone go through a conditioning process, whether it's classical or operant conditioning, usually operant conditioning, we can learn vicariously through them. So if we think of two rats, we have a model rat that's in an operant box, and they're pressing a lever to get food. If we have an observer rat who's just watching the other rat, they might start to make an association between pressing that lever and getting access to food. Though our observer isn't actually experiencing it themselves, they might make some connections based on what they've seen someone else do. And so we can actually break this process down into 4 distinct phases. And this is where we start seeing some weird terminology again. So I'll use a couple of options here. But phase 1 is attention. So our learner is our observer, the one who's watching. And our model is the one who's called a trainer sometimes. I prefer model because they're modeling the behavior. But if we think of them as showing that behavior to our observer, trainer kind of makes sense. But our attention stage is basically saying, is our observer paying attention to the model rat? Are they watching what the other rat is doing? Retention, our second stage, asks, is that observer thinking about or sort of making some connections in regards to the behavior that our model rat was expressing? So when that model rat pressed the lever and got food, our observer should be watching, paying attention, and forming some kind of connection, retaining some of that information to act on later. Our next stage is production. So this is when our observer gets the opportunity to produce that response themselves. So we move our observer into their own operant box. We give them a lever and the opportunity to press that lever. And then we also have a stage of motivation where when they press that lever, they should be reinforced with food just like the model rat was. So we would make it more likely for them to continue doing that behavior in the future. So this process could actually help us, say, skip things like shaping because they're learning to make these connections, to do this behavior by watching someone else do it. And there's lots of really cool research on this topic. One of the ones I've been reading lately comes from the U of A, where they were looking at observers and modeled behavior in nest building with zebra finches. So they had model zebra finches build nests, and the observers would choose to copy their choice in nest material based on a bunch of different factors. And we can look at what makes them more likely or less likely to copy. So there's lots of really cool research in that area nowadays. So some interesting stuff going on. But that's just sort of the basics of our observational learning. And then if we wanted some sort of concrete evidence beyond some of our behavioral studies, we can actually look at some neurological indicators for this kind of observational learning. And these are mirror neurons. So they're neurons that are activated by both performing an action and watching someone else perform that action. So it's kind of like there's a part of our brain that responds to us doing a particular behavior, but also to seeing someone else perform that behavior. So we can link or kind of imagine us doing that behavior while watching them do it. So we typically see this in sort of simpler systems. There's a lot of research on these in, say, rats and even primates. But there's less work in humans, probably just because our brains are a lot more complex and our activities are a lot more complex. But there's a lot of really cool research there as well. And of course, we can't talk about observational learning without talking about one of those core pillars of weird psychology experiments from the past. So maybe you've heard of the Bobo doll studies, or maybe you are just being exposed to this nightmare fuel for the first time. But this was a very famous experiment looking at aggression and specifically learning aggressive behaviors in children. So the setup here is that they had these Bobo dolls. You might have also seen them called like Weebles. They're really heavy at the bottom, and so when they sort of tip back and forth, they don't fall over. They will right themselves because of that low center of gravity, but it allows you to sort of interact with them and push them pretty aggressively, but they'll always stand back up again. So they used these Bobo dolls that were sort of impossible to tip over and terrifyingly painted to look like clowns. And they were having sort of a model, which would be an adult, interacting with the doll. And they'd have observers, so children, who would watch the adults interact with the doll. And of course, we care about aggression. So we were looking at what happens if an adult walked in and acted aggressively towards this doll, especially if they were aggressive and they were encouraged for their aggressiveness. So if an adult walked in and punched the doll and somebody else laughed or said, "Do it again," the children would then be very likely themselves to copy that behavior when given the chance to interact with the doll. And if you look closer at some of these images, these kids went nuts at these dolls. There's a lot of videos of this. So if you wanted to take a few minutes on YouTube, they have a lot of sort of commentaries on these kinds of studies, and they're very entertaining. But they also found that it worked the other way, where if an adult was aggressive towards the doll and was then scolded, the children were then less likely to be aggressive themselves. So lots of evidence there that children watch adults and also learn from the consequences of the adult's actions when deciding how to behave themselves. All right, so we have 2 slides left. The first is going to be just a brief reminder of this concept of biological preparedness. So we talked about this first in our classical conditioning, and we mentioned that it's easier to form associations between certain types of stimuli and certain types, or I guess between certain types of stimuli, period. There's also sort of a biological preparedness to form associations between certain types of stimuli and certain outcomes. So it isn't just classical conditioning that preparedness can be set up for. It also works with operant conditioning. And also we can have things where we are set up to learn like social behaviors as well. So biological preparedness isn't a classical conditioning alone kind of learning. But we basically have this idea that some events are better signals or better conditional stimuli or better whatever than others based on evolutionary traits. So we have predispositions, sort of innate pathways that make some things easier to learn about than others. And one of the fun examples of this that we can run into where actually biological preparedness causes problems was trying to condition raccoons, operant conditioning, there we go, keep the words separate. Operant condition raccoons to put money in a piggy bank for a commercial. So someone was trying to film a car commercial. They wanted a raccoon to take a coin, put it in a piggy bank. And what they were doing through the process of shaping was getting them to sort of pick up the coins, put the coin in the piggy bank, and then pick up another coin and put it in the piggy bank too. And they were being reinforced with food. But the problem here is that food has these biological predispositions. We have certain behaviors that are already associated with food. And if you've ever watched raccoons with food, one of their behaviors associated with food is to sort of rub their hands together with it. So you might see where this is going, but the raccoons were okay with one coin, more or less, but as soon as they introduced a second coin, the raccoon took one in each hand and rubbed them together and refused to let go of them. So we run into this issue where as soon as that particular action is associated with food, it activates other pathways associated with food and can lead to problems. So they never did condition the raccoon to drop the money in the piggy bank because they couldn't get past that. And then the action of rubbing it together itself became reinforcing, and they just had to find another way. But there's lots and lots of examples of stuff that we sort of are predisposed to learn depending on our situations. And then our last topic here is to discuss very briefly the idea of learned helplessness. So this ties back to what we had talked about earlier with escape and avoidance conditioning. And so learned helplessness is kind of like when we have an escape conditioning setup, but we're not actually able to escape. So if you experience an aversive situation that you don't get any control over, something that you can't escape or something that you can't avoid, it can actually prevent you from learning anything about escaping or avoiding that situation in the future. So if we think of those shuttle boxes I was talking about before, a normal escape response would be if there's a really loud sound on one side, you would go to the other side of the chamber where it's quieter, you go into the other half. In a learned helplessness setup, they would put a clear wall between them so you couldn't escape. And eventually, all sorts of different kinds of organisms learn that I have no way of escaping, so I'm not even going to bother. Then if you remove the barrier, those animals still stay in the place with the aversive stimulus because they've learned that it's not worth trying. And so even when presented with new situations, new information, they stay put. And so a lot of the learned helplessness research nowadays starts making connections to things like depression, where if we're in a situation where we've learned that nothing we do helps, we might stop trying to overcome that situation. So even if we get new resources, we might stay stuck. So a lot of the new research in learned helplessness is looking for ways to sort of disrupt that system. How can we introduce that desire to learn to escape these situations even after we've set this up? And so a lot of cases, it would be something like forcing them to move to the other side so that they realize that it's better on the other side, whether you physically move them or set it up in some way that can help overcome this. But there's a lot of really neat research in that area as well. But that's what I wanted to cover for this chapter. As I mentioned last time, I wanted to get through all of this for today so that there's no new content for you to learn for the midterm. That means that on Friday, I'm going to talk just a little bit about doing operant conditioning in an actual lab. I'll show you how we did operant conditioning with chickadees. And then with our leftover time at the end, I'll allow people to ask questions. So if that's something you're interested in, you are welcome to be here. And then if not, then you don't have to be here, and then I'll just see you on Monday. But that is the chapter.